Welcome to The Explainer. In this guide, we are diving deep into material engineering. If you're studying for an exam or you're just curious, we're going to give you a really solid framework for understanding how we create the incredible materials that shape our modern world.
So let's kick things off with a big question. How do you make something hard enough to cut steel, but also tough enough that it doesn't just shatter on impact? It sounds like a total contradiction, right? Well, the answer is all about the amazing science of manipulating materials both on the surface and deep down in their core. And we're going to break down exactly how engineers pull off that incredible balancing act. So here's our game plan. We're going to follow the journey of a material. First, we'll look at its protective surface, the armor. Then, we'll go deeper to its internal structure, the core. After that, we'll see how we prove it works. And finally, we'll take a peek at the amazing stuff that goes way beyond traditional metals.
Okay, let's jump right in with Part 1, Applying the Armor. This is all about how we beef up a material's exterior, creating this tough, functional shield, all without changing what's going on deep inside.
Think about the gears inside a car's transmission. The center of the gear has to be tough, right? To handle all those shocks and jolts. But the surfaces of the teeth? Oh, they need to be ridiculously hard to keep from grinding away. That's the magic of surface treatment. You're creating this incredible high-performance skin without making the entire part brittle.
Basically, there are two main ways to do this. You can change the surface itself, like with carburizing, where you basically soak the surface layer of the steel with carbon atoms to make this super hard built-in case, or you can just add a totally new layer right on top, like electroplating chrome onto a bumper to make it shiny and rust-proof. So one modifies the original, the other adds a new coat.
And when it comes to that final finish, you've usually got a trade-off. Do you need an industrial-strength shield, or do you need more flexibility? Powder coating is the shield. It's a thick, dry powder that's sprayed on and then baked into this incredibly tough plastic shell. Painting, on the other hand, is more like the artist's brush. It's way more versatile, but it's just a thinner, less durable layer.
You know, this analogy really makes it click. A coat of paint is like a thin layer of varnish on a wood floor. It helps, sure, but powder coating? That's like pouring a thick layer of epoxy all over the floor and then baking it solid. You're creating a completely separate, hard shell. It's a whole different level of protection.
So, that's the armor. Now, let's forge the core. For Part 2, we're going deeper than the surface. We're going to use the incredible power of heat to basically rewrite a material's internal DNA.
You know, no matter what you're trying to do, every heat treatment follows these three basic steps. You heat it up, you let it soak for a bit so the temperature is the same all the way through, and then you cool it down. But the real magic, the absolute secret sauce, is all in that third step, how fast you cool it.
Just by controlling that cooling speed, you can get these three totally different results. You can anneal it, which makes it super soft and easy to shape. You can harden it, which makes it incredibly wear-resistant but brittle, like for a drill bit. Or you can temper it, which is all about finding that perfect sweet spot, that balance between toughness and hardness that you'd want in something like a hammer.
And this table just lays it out perfectly. Look at the cooling method. It dictates everything. For annealing, you cool it down very slowly, right inside the furnace. That gives the atoms time to relax into a soft structure. For hardening, you do the exact opposite, a rapid quench in water or oil. That shock freezes the atoms in a chaotic, hard structure. It's amazing. The cooling speed is everything.
Okay, quick pop quiz. Great for anyone studying for an exam. If you need to make a piece of steel softer so you can machine it, which process are you going to use? Is it A, B, or C? If you said B, annealing, you are absolutely right. That ultra-slow cooling is the key to getting the softest, most workable material. This is such a perfect way to think about it. Firing clay in a kiln makes it incredibly hard, right? But it also makes it brittle. If you drop it, it's going to shatter. That is exactly what hardening does to steel. And that's why hardened parts almost always have to be tempered afterwards, to trade just a little bit of that hardness for a whole lot of toughness. So we've armored the surface, we've forged the core, but how do we actually prove that it all worked? How do we know the material is as good as we think it is? Well, welcome to Part 3, Testing the Limits.
When it comes to testing, engineers have a huge choice to make. Do you take one piece and literally break it on purpose? That's destructive testing. You get exact numbers on its limits, but you sacrifice the part. Or do you inspect the final product without leaving a mark? That's non-destructive testing, or NDT. It's more like a checkup to make sure the part is good to go.
And here are a few common ways they do it. To find the breaking point, you can pull a material apart in a tensile test, or you can smack it with a pendulum in an impact test. To find hidden flaws without any damage, you can use ultrasound to listen for echoes bouncing off internal cracks, or even use X-rays to see inside, just like a doctor would.
This car analogy just nails the difference. A car company will perform destructive testing by crashing a few cars into a wall to prove the overall design is safe. But when you go to buy a car, you want NDT. You want a mechanic to inspect the engine and frame to make sure your specific car is safe. And you definitely don't want them to crash it to find out.
All right, for our last section, let's look ahead. We're moving beyond traditional metals into the really exciting world of engineered materials. This is the new frontier, where materials are being designed from the ground up to do incredible things.
So much of modern tech is built on these three pillars. You have polymers, which is a fancy word for plastics and rubbers like the nylon in your jacket or Teflon in your pan. You have ultra-hard ceramics, used in things like cutting tools and medical implants. And then you have composites, where you mix materials together to get the best of both worlds, like carbon fiber, which is lighter than aluminum but stronger than steel. It's amazing stuff.
And looking forward, things get even wilder. We have smart materials that can actually react to their environment, like alloys that remember their shape. We have advanced materials like synthetic spider silk that's stronger than steel. And, so importantly, we have biodegradable materials, made from things like bamboo or even mushrooms, that can return safely to the earth when we're done with them.
Okay, we've covered a lot of ground, so let's boil it all down. What's the one crucial thing to remember from all this? How can you organize all this in your head?
It all comes down to this simple four-part framework. First, you protect the armor. Then, you forge the core. Next, you need proof that it works. And finally, you explore what lies beyond. Armor, core, proof, beyond. If you can just remember that sequence, you've got a mental map of this entire field.
And this leaves us with a final, pretty mind-bending question. As materials get so advanced that they can heal themselves, sense their own damage, and adapt, where does the material end and the machine begin? The line gets really blurry, doesn't it? The very substances we build with could one day be just as intelligent as the things we build. Just think about that.